All right, so this is in section 3, mostly machine learning for text or sequential type of data. And this is the beginning lecture of section 3, lecture 16, and generative base classifier. We are in module 2. So in this module, I will talk about naive Bayes classifier. And next, I will reuse some of my last year's recording. All right, let's get started. So in the module 1, we explained about the probability with full tabular formulation, but that's not very feasible.
That you have to have a lookup table of 2 to the p times the L number of classes to perform the previous lookup type of discriminant random variable generation. That's not feasible at all. The whole reason is, there are just too many things here. Like 2 times 2 into -2 equals to 2 to the p, then times the number of possible classes. You need to memorize this through estimating or counting from your data. And then later, when you have a future data, you need to search, or actually not search, retrieve a specific case from this 2 to the p times L lookup table. This is not feasible. So that's why people have some kind of simplified assumptions, which the mostly used is called naive assumption. The whole naive assumption is extremely actually simple. I'm assuming all the input variables are conditionally independent given the output variable. So equation-wise, it's really easy. It's just the join probability. So actually now we only do this part. So this is a join probability, right? It's a join probability of x1, x2 onto xp when conditioned on the cj. So it's a join probability. And I just assume all this variable are conditionally independent from each other. If you still remember the conditional independence assumption, which makes it equivalent to when you're conditionally independent, this join probability equals to a multiplication of each variable conditioned on that specific class variable. And I don't need to do the joint anymore. I only need to just estimate x1 condition on cj, x2 condition on cj until xp condition on cj. So, and this is exactly that part. This is a simplification. So it's not because this exists, right? This is my assumption. I'm assuming the join probability equals to the multiplication of each. All right, so now this part is super easy to do the calculation. Now go back to the graph. So what do I mean the models now if I have this assumption? So what is my model now? What do I learn from my training data? So let's see, whenever, we had that before, to perform PCJ condition on x1 onto xp, and that's my classification rule, right? And I need to use this is px1, x2, xp condition on cj times pcj. And now it's equivalent to px1 condition on c, px2 condition on c, until pxp condition on c, cj, specific cj, and then times pcj. So this is the model I need to estimate from data, which means to perform future inference, I need to know this, 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 and this. And this is the model parameter I need to estimate for my naive Bayes classifier. And when you have a future sample has specific values, and then you just look up. So again, this is still a lookup operation, but the lookup operation is, I think I have a page, yeah. So maybe let me write it here. So what I need to estimate from data now is from training data is PC. It's actually in fact this. It's just exactly this. And each one of this is a table, right? So go back to see your current, that table. How many parameters do I need to estimate from the training data for this? How many for this? How many for this? How many for this? And this is the same thing, right? Still P yes and P no. Let me actually add a page because I think it's important. Yeah. Yeah, so okay. Stopping and responding, but I think that's okay. So yeah, I think I can stay right there. Yeah. So in the end, to be able to, as when there's a new data coming in, I need to look up this. I need to look up this, and then I need to look up this until look up this, right? This means the thing I need to estimate from my data becomes for x1 and condition C, yes, and condition C, no. How do I write easily? So x1 has how many cases? S, O, R. Yeah, okay, so it's the C. So I need to estimate this, right, from data. P x1 condition C. And the x1 equals to S. X1 equals to, sunny. And then x1 equals to overcast. And then x1 equals to gray. And one condition C is yes, C yes, C yes. And this is the one I need to estimate from data. So let's just use an example. What is sunny given yes? When you look at your table, what is sunny given yes? So there are a total of 9 cases in the yes, right? Which is equivalent to number of sunny and yes over number of yes cases, which is equivalent to, it's a little bit hard to count, 2 over 9. Yes, 2 over 9. Yeah. And then you just do the same for O and yes, and R and yes. And then you do the same thing, S, O, and R for C equals to no. And this time, it's just the number of counts, sunny and no, over the count of no. What is it? Sunny and no. Sunny and no. is how many, Sunny? 3? Is it 3? 3 over 5. Okay, and this is, you just perform the same operation on x1, x2, x3, x4. And then you also need to have p c equals to yes. Without anything, it's just that's called prior probability. P c equal to no. What is it? I think we already had it. Is 9 over 14 and 5 over 14. And this is your naive Bayes classifier model. And this is exactly what you're going to implement in the homework. And the only difference is our x1 until xp are English words. And you need to count. You need to count how many times, how many samples that word appear, and also the class label is maybe positive sum up over the number of positive articles. All right. Okay, so this sounds so easy, right? But it's the procedure is important. All right, and then when you perform, this is the same thing. And in fact, what I did there is by assuming this is a Martinoli distribution. The whole thing I'm using counting is the Emery solution by assuming this is a Martinoli distribution. When the binary case is Bernoulli distribution. But actually, there are many other possibilities, which one of the possibility is called multinormal distribution, which is used the most in the bag of words representation based naive Bayes classifier, which we're going to cover next lesson. So there's whenever people use bag of words representation, they normally assume, so this is my word, maybe good, condition on sum up. So they're not just care about exist or not exist. What they care is number of times it exists. And how do you represent when this is an integer or it's a frequency? We can't just do this count-based MLE. It's not completely correct. So in those situations, it's not being assumed as a Martinoli distribution anymore. They need to use a multinormal model to represent. So there are some differences and which we're going to cover in detail next lesson, especially bag of words representation is using, we need to use multinormal distribution to model bag of words representation. All right, so in the learning phase, you really just count. So you count the prior, then you count each possible values by condition on all the different all the different class output cases. Then let's calculate how many parameters you need to estimate in this. So let me come back to this example. Okay, so for x1, how many examples do I have? How many parameters do I need to estimate? One, two, three. 3 times 2, right? 3 possible values, and then L possible class. So for the first, it's 3 times L equal to 2. For the second feature, same thing. 3 times L, 2 times L, 2 times L. Okay, so in total, how many parameters do I have in a naive case? 3 plus 3 plus 2 plus 2 times L. So it just in our case, L is 2. L equals to 2. How many parameters? 20. Yeah, it's 20, right? Okay. And plus the 2 prior, plus 2. In total is 22 parameters. So versus the previous case without the naive assumption is 72 plus 2, right? So that's the no naive case. Is 72 plus the 2 prior, which is 74 parameters. And in this case, we have plus 2, the 2 prior is 22 parameters. So we have much fewer number of parameters. Okay, now let's make it even more extreme. If I'm doing x1 until xp, each one of them have only 2 cases, 2 possibilities, x1, x2, until xp. How many parameters in this case I need to estimate? Each one of them have only 2 possibilities. 2 plus 2 plus 2 until the pth case. So in total, this gives me 2p, right? And then times the L. That's because for each class you need to generate, you need to have that condition on each possible class. So this is, let's do the class until this give me 2pl. And this is versus 2 to the p times l in this non-naive case, right? And you can tell, and there's a reason why we need to have the naive assumption. So even if p equals to 30k, how many parameters do you need to estimate if this is 30k? Assuming L is 2, 120k parameter to estimate. And this is still feasible when you have large enough text samples. P 30k is feasible if you do the naive assumption. All right, so this is the key, the whole thing about the naive Bayes classifier. Lookup table. Yeah, so I already talked about it. And then when you have, you can do Bernoulli, binomial, and then, So this is a more generic case, right? Assuming the first feature has K1 possibility, K2 possibility onto KP. It's really a summation of K1 to KP times the L. And then during the testing phase, what do you do? And there's an input number of X, and then you just calculate P A1 condition CI, A2 condition CI, until AP condition CI. You multiply those things you got from the lookup table and times the PCI, and then this will have C1 until CL numbers. Whoever give me largest of this number is the predicted class label, C star. So in fact, this type of naive Bayes assumption can be used through a graph type of representation. It's if my variable, if the parameter I need to estimate it is conditional on some variables, and I write those variables as my parent. And the naive Bayes classifier can be represented by this simple diagram, graph diagram is, I need to estimate, because the C has no parent, right? I don't need to estimate anything. I only need to estimate PC. That's exactly it was trying to show, PC, because each of these X features, they are conditioned by the parent of C, and then I need to estimate for each one of them, the variable I need to estimate is the possible values. Let's use X6 as example, X6 into some kind of maybe X61 possible values, conditioned on the CI. And for this type of edges, we just need to estimate all the combinations of the values from X6 versus the values conditioned on the values of all the possible C, which is exactly those naive conditional probability we are learning. So this whole diagram shows everything about the naive Bayes classifier. We need to estimate PC, only PC, and then we also need to estimate Px sub j of specific values conditioned on each possible C, Ci. Oh. Yeah, maybe K, maybe P. Yeah, it's some kind of possible values. Yeah. Let's just see hot or cold or whatever. Yeah. Okay, so the whatever I did before, it's essentially assuming this as a Multinormal distribution. That's why the parameter estimation or MLE solution can be estimated through counts. So the number of xi is the specific values at the same time. C is a specific Cj over the number of times the specific Cj exists in your training data. Yeah, so this everything we covered. This PC equal to C, Px condition on C, and then you just and this tells you this diagram guarantees x6 and x5 or all the x are conditionally independent from each other when given the C variables. It just because we have a shared parent C here. So this is just called a graphical model of BaseNet representation. So if you don't completely get it, don't worry. I just want to give you some kind of more advanced version to talk about Bayes model. So because I'm showing you a graph, right? And then there's something means, and this is the simplest tree graph. But in fact, you can have a lot more complicated, right? So this is so easy. All in C controls x1, x2 until x6, but maybe your data is not this way. So maybe your data is assuming I'm trying to predict a child diabetic or not. And there will be some parameters, some features are dominating parameter like age parameter. The age feature versus maybe weight. Let's think about age, weight, and disease stage. C is the diabetic or not, and there's maybe, I'm too slow today, but the age and weight. So if we have only the naive Bayes model, the correct diagram is age and weight, only condition C, right? But in fact, that's counterintuitive because the weight of children clearly will be also dependent on the age too, right? So this, and just the one we show you is the simplest ever, only naive assumption. But in the real world data, the relationship of among the feature variables and also relating to the output variable is much more complicated. And this type of relationship is called BaseNet. When you learn it, you actually can learn the relationship among features from data, not just using the simplest naive assumption. All right, so this is what I showed you, the lookup table view in the naive Bayes classifier, and I already did. These are the parameter two. They're also lookup tables. And then you can do the calculation that we did. Then the whole thing is counting. And then there are a total of 20 parameters we already did. Yes. Then in the testing phase, let's give you an example is SCHS, and you want to predict based on the naive Bayes classifier. Then how do you do? In fact, you just look up. You look up what is the PC1, yes, and what is PC2 or no. You just get those numbers from that table, prior probability table. You also look up what is P sunny given C1, what is P sunny given C2. what is P cool given C1, P high given C1, P strong given C1. You got to look up from those tables, you do the calculation, the same thing for the C2 class, the no class, and then you just get the numbers. The first give you 0.0053, the second give you 0.02, and this is bigger. So that's why we predict this as no. Is it clear? This is completely how you're going to implement in your homework, to implement a base or naive Bayes classifier. I think we're pretty good because I already covered without assumption you have 2 to the p. With assumption you have 2p times c. Yeah, 2 to the p times l, 2p times l. And this is linear to the number of parameters. This is exponential to the number of parameters, which of course exponential is not scalable to the large p. And I think the last is 1 minute, is one thing. There are situations like this. Assuming there's X6 is muscle ache, and the C is with flu or without flu. There are situations because you have to estimate muscle ache, if muscle ache equals true condition on flu or not flu. But maybe in your data, there's no muscle ache, but no flu. And that makes the count of this as 0. This is a probability 0 case, right? They give you probability 0. Why this is actually extremely bad. The reason is when you're performing the prediction classification, you have to do PC equals to flu, X1 condition on flu until X6 condition on flu. And then also PC equals to not flu until the PX6 condition on no not flu. If any of the numbers there is 0, it doesn't matter what the other numbers are. It will be just dominated by 0. So this type of naive Bayes classifier for the discrete case, you have to try to avoid 0 probability. And because it doesn't work when you do this multiplication, joint probability estimation, and you have to try to avoid the 0 probability. But there's a lot of cases we actually did. I have this SO whatever cases coupled with output yes. It just not exist in my training data. It doesn't exist, then how do you do with it? There's a lot of trick called smoothing trick. Simplest trick is you just +1 on the denominator plus maybe the number of possible values in the denominator, and this can give you a good, at least good baseline for the non-zero case. There's a lot of different the Laplacian smoothing, there are actually many types of smoothing, and this is one of the very big topic in information retrieval and natural language processing. And to summarize, we are trying to predict using probabilistic models and using through the MAP rules, because the P, it's for the discrete case, the number of parameters to be estimated from the data is exponential to the P. So that's why we have a naive assumption to make the number of parameters linear to the P. And next time we're going to talk about Gaussian Bayes classifier, because here I'm assuming all the variables as discrete, either Bernoulli or Martinelli variable. But how do you handle when it's continuous, right?
Great. So this is the end of this module. See you in next module.